Okay, welcome STEM students to the second class period of STEM class. I'm very happy to be doing a recorded lecture. So what we're going to go over first is just some of the stuff that y'all completed for the homework. So y'all did lab reports, great job overall. I wrote comments of the stuff that y'all can improve on. If I didn't write a comment, it means that it was good enough to pass as it was. So congratulations on that. So you just find the comments on the right hand side over here. I'm not going to go over the different students' comments in class. So just look at that afterwards. It's also part of the homework for next time. On this experiment or Google Sheets homework that y'all did, I wasn't satisfied because of one reason. There was the x-axis has the data all over the place. So you can see that we start with 35, go down to 25, 1, 8, 15, 7. It's not in any kind of order, and that's really bothering me because you can't really look at a graph that well and tell what you're supposed to see. So we need to be able to sort this. So the first thing to do that is I had my averages and totals over down here, right? I had to delete those to be able to sort it. Then you just left click there, right click over one of the cells, sort range. Make sure you click data has header row because we have the headers up there, right? We don't want those to be sorted. A to Z, that also means ascending, so it'll give us from youngest to oldest. Oops, not that. So what we're going to sort is by age, right? That's the second column over here. We're going to sort it by age. So we just hit click and that'll sort it out for us. And then that automatically also corrects the x-axis, right? It looks much better now. You can see a better correlation between age and height there. So y'all don't need to change this. I just wanted to show you how to sort data there. It was bothering me because my graph was looking terrible and one of the students was looking pretty good. So I just saw that and I wanted to improve and show y'all another technique. So what we're going to be going over today is engineering through a look at Newton's laws. Hopefully y'all have seen Newton's laws before. If you haven't, well, we're going to dive into them today. So the terminology for today's lecture involves acceleration. Let me get my pointers out. Pointer options. Ooh, I love the pen. So acceleration, the rate of change of velocity per unit of time. It's a little bit of a mouthful, but if you have speed, right, if you're traveling 5 miles per hour, then that's constant, right? If there's no change in acceleration, or there's no change in speed, that's constant acceleration, meaning that you're going the same speed the whole time, 5 miles per hour. If you speed up from 5 miles per hour to 10 miles per hour, then your acceleration increased for a while. But if you continue going 10 miles per hour for a while, then there's no more acceleration. So you need acceleration to go to 0 miles per hour to 10 miles per hour, or any speed, right, that's greater or even below 0. So you need some acceleration to get from that point to that point of miles per hour. Just put m over s, even though m stands for meters and the science world. So let's just say that's meters then. 0 miles or meters per second to 10 meters per second, you're going to need some acceleration. And the acceleration is the rate of change of velocity per unit of time. Another important piece of terminology here is mass. Now, as Americans, we use pounds, but pounds is actually a weight. It's not a mass. So a mass unit in the US system would be a slug. And a lot of people don't even know what a slug is, but it's the mass unit. So what is mass? It's a measure of the amount of matter in an object. So let's say we have this ball right here, and that all we mean by mass is how many atoms do we have inside of this ball. So it's going to have the same amount of atoms here on Earth and the same amount of atoms on the moon, this ball will. Let's just say it's solid so that the air compression doesn't play anything with it. So it's like a shot put, let's say. Same mass on Earth, same mass on the moon. Weight is different. Weight in the US system would be pounds, and weight in the metric system would be newtons. So it's going to weigh different pounds and newtons because it's subject to a different gravitational force, which we'll get a little bit more into that later on. So it's a different weight, but it's the same mass. So just keep that in mind. When we look at the periodic table, we're constantly being introduced to the mass of an object. Acceleration, here's some acceleration examples. Hope you look at those to understand what I'm saying. So those are the terms that we're going to use in this unit here. So next I want to go through the differences between engineers and physicists. So physicists are scientists, right? And scientists wonder what something is. So we look at this down here. Does anybody know what it is? Did I hear someone say blobfish? I'm just messing with you. Yeah, it's a blobfish. It lives in the ocean. It looks pretty weird. So scientists wonder, what is this? What is it made out of? What kind of chemicals? Well, what are the importance of these chemicals in the science realm? And then engineers would look at it and would look at the blowfish and be like, oh, can we stuff this inside an engine crack and will it stop it from leaking oil? Or can we use this, does this look like boogers and can we use boogers for something? So they want to know not just what it is, but how they can use it to solve a real life problem because they want to solve problems. It's kind of like a real dominance thing, you know, you solve problems, you gain the real. Okay, so Newton's first law here. So Newton's first law, the law of inertia, states that an object in motion or at rest will tend to stay in motion or at rest until it is acted upon by an outside force. So please write this down in your books. We're going to write down the 3 laws today. What does inertia mean? It's a property of matter by which it continues in an existing state of rest or uniform motion in a straight line unless that state is changed by an external force. So let's say that there's a ball traveling in a vacuum in space. In that case, I'm pretty tempted to say that there is no forces acting on it. There's no gravitational force acting on it. There's no frictional force inside of a vacuum. There's no air molecules. So it's just going to keep going inside that vacuum until it hits the side of the vacuum. But honestly, everything in this universe that I know of, I could be wrong, and I'm welcome to be wrong, but as far as I can tell, there is a force acting on everything. So Newton's first law, though, just means that something will be in motion until it has a force acting on it. So let's look at this little example down here of this teacher and the kids here. So if you've seen kind of a pendulum, it'll swing back and forth until it finds its resting place in the middle. And that's kind of what kind of goes on here. This kid hits this kid, who then hits that kid, then hits the other kid, the other kid swings out, comes back, and then the process is repeated in the opposite direction. This kid spins back out, comes back in, but eventually they will stop hitting each other. They're not going to stay in motion forever, which would be called perpetual motion, which does not exist because there's always a force acting here. So let's try to think of some of the forces acting here. When this kid hits this kid, something happens. When you hit something, there tends to be a collision, right? Or there is a collision. And that usually makes noise. So some of the energy of the kid moving is lost to noise. It changes from a state of motion into a state of noise, which is still motion. It's just not the kid's motion anymore. It's the air molecules vibrating now. So you lose some to noise. The chains at the top, there's friction as they hit the joints up there, so you lose some to that also. So it's being acted on, right? The object is in motion, the kid is in motion, but it's being acted on by an outside force here. And that's just Newton's first law, is that it'll stay in motion until it's acted on by something else. Newton's second law. So Newton's second law states when an object is acted on by one or more outside forces, the vector sum of those forces is equal to the mass of the object times the resulting acceleration vector. So we have exactly what that states down here. This is the force, and this is the mass times acceleration. Now, if I was teaching a physics class, we would just dive into this and stay on this for the rest of the lecture and many more lectures, but we're not going to get too overwhelmed with this. It just means that you have to look at the sum of all the forces on an object, just like we did in the previous slide with the kid, right? We were looking at him being pushed by the teacher, and then he hits the other kids and the forces going on there. So we have to look at all the forces and add them up when they're acting on an object. Now, force is the measurement of weight of something, right? I was saying that earlier, pounds and newtons are the same. So in the metric system is what they use in physics. Acceleration is distance divided by time squared. So distance divided by time squared. And the metric units for distance, does anybody know them? I said them before. And if you said meters, you are correct. So it would be meters divided by time squared. So the units and the metric system would be seconds squared. So that's our acceleration units. And then for mass, like I said before, it's a measure of how much of a thing, and the unit for that would be kilograms, and the metric. So we have kilograms times mass divided by seconds squared. That would be the force of an object, or the weight, right? So that's that. So we have to look at the total here. So what is happening in this system over here is this box down here, the force acting on it is gravity pulling it downwards. So because it's attached to a string and pulley system to the other box, if the force of gravity is bigger than the frictional force on this table, then the whole system will start moving this way and downward. If they're equal to each other, if the frictional force is equal to the gravitational force, then it's not going to move at all. So that's Newton's second law, is we have to look at all the forces acting on a system, right? Newton's third law. For every action, there's an equal and opposite reaction. So if you push on this wall with 1 Newton of force, it's going to push back on you with 1 Newton of force. If you do it with a lot of force, it's going to hit you with a lot of force. It's always going to be equal and opposite on you. So if you push too hard, you're going to smash your finger in and really hurt yourself, because I'm pretty sure a brick wall that is cemented is not going to budge with your finger. Let's say that you're running down the field and there's another person standing there, and this person is way bigger than you. We'll denote that with bigger feet, I guess. And you run into that person and he doesn't even budge. You're running so fast, so you had an acceleration, right? Because you're running towards him, and you weigh something, but you're smaller, so your mass is smaller. So your force is smaller, because force equals mass times acceleration. So your mass was smaller than his, so that's the down arrow, it means it's smaller. So this person doesn't budge. So let's say that you hit him with 10 newtons of force. Take a wild guess on how many newtons of force he's exerting on you. Your force would be pointed in this direction. His force will be pointing in what direction? If you said the opposite direction of the other person's force, you are correct. His is 10 newtons, and he will be exerting 10 newtons of force against you. So it's going to be a very painful collision, because now there's 10 newtons plus 10 newtons going in the opposite directions. So it would be 20 newtons of force total there. So that's the laws. We can only do 10 or 15 minutes of video, so I'm going to create the second video. So just go ahead and click on that link and we'll finish up the lecture for today.